very much. Very kind introduction with the crew, and also I'd like to thank for giving me a very nice opportunity to talk about my chemistry from Osaka. So, actually I'm a Korean born in Japan, so I should speak Korean language here, but some problem. So please accept the station. So the thank you. Okay, next slide, please. So I'm synthetic chemist, one chemist. So I'm not a professional in dealing with ionic liquid, nor I'm not a professional in dealing with microflow system. But simply, my mind is one day I thought why we are still using organic solvents. Why? And also, why we use glass reactors always. That's such occurrence is the beginning of my my research in this area. So today I'd like to talk mainly two topics. One is Pd-Catalyzed coupling reactions, which is very nicely, which works very nicely when we use ionic liquid, especially Sonogashi coupling reactions. And also the second part may be the application of the reactions using microflow system. Next slide, please. So this part I don't. It's not necessary to repeat this part. So BM, IM, PF6. This is the most commonly used ionic liquid, and also this BF phosphate was also used frequently. And what we learned here is, and these ionic liquid has a highly polar, so polar aprotic solvent. When synthetic organic chemists would like to use polar aprotic solvent, we rely upon the DMF, and then we stopped. But these ionic liquid give us more opportunities to test more polar ionic solvents. Next please. And this is a brief summary of the original work in this area. So this is Professor Sedon's work, which published in 1999 in Organic Letters. This is 1 year ago. I checked the cited number. It's 167. So probably now it may be 200 or so. So highly cited. One of the highly cited paper. And he did the work. He applied Misoroki-Heck reactions. So it's a famous reaction, cross-coupling reaction using palladium catalyst. And they use BMI and PF6. And after the reactions, reaction mixture was treated with hexane. And hexane can extract the product, ester. And so the palladium catalyst is immobilized in the ionic liquid layer, and after the washing with water to remove the ammonium salt, so they repeatedly use this BMI and PF6 solution containing palladium catalyst, and they ran an excellent result even after 6 cycles. Next, please. So why the palladium catalyst is immobilized in ionic liquid? This is simple. So ionic liquid can react with palladium species to make palladium carbon complexes. So these palladium complexes have a ligand. It's a similar ligand like a solvent. So it's quite natural to be immobilized in the solvent. So these Chinese chemists did a nice work of this reaction, and they observed that 4 types of the complex, palladium complex, are formed in this reaction system. Next, please. And as Professor said already, talked about the Grubbs catalyst. Grubbs, the Nobel Prize winner of chemistry, and the Grubbs catalyst can be immobilized if there is a ponytail having the tornium salt very nicely. So these two groups published a paper almost at the same time based on closely related ideas. And they repeat the reaction after 10 cycles, still the catalyst activity lasts. Next, please. And this is the work by the Sodeoka. Sodeoka is a female chemist in Japan, very nice chemist. And she applied binap-based chiral palladium catalyst and for fluorination of alpha to carbonate portion, enantioselective fluorination reactions. And since this catalyst is very expensive catalyst, they use HMIM BF4 as a solvent and a catalyst support. And this is a cationic complex, but well supported by, this is a cationic palladium complex. This is well supported by this ionic liquid. Next, please. And even not the cationic complexes, this ruthenium binap type complex can be immobilized in PF6. But in this case, supercritical CO2 is used after the abstraction of the product. So if they use an organic solvent here, probably this catalyst may be reached to the organic area, organic part, but the supercritical CO2 completely separation was completely done. And this work was reported by Jessop at Queen's University in Canada. Next, please. So we were interested in the use of ionic related system for Sonogashira coupling reaction. Sonogashira, Professor Sonogashira was a staff of Osaka University, and he moved to Osaka State University and now retired. And he did a very nice work in the area of cross-coupling reaction. So to make acetylene compound from the arene vinyl halides with alkynyl arene vinyl substitute and terminal acetylene compounds. And so that reaction has a lot of applications which include natural product synthesis and also some very important material synthesis. And the unique system is they add kappa co-catalyst here. Kappa co-catalyst here. So binary system is catalytic system is you employ for the original Sonogashira coupling reaction. Next, please. So the reason why the kappa is necessary is obvious. So to make the alkyl should be at the palladium center. So this transfer step is not so easy. So they use a kappa co-catalyst to make kappa acetylide. And then the kappa acetylide can deliver alkyl to palladium center. Then reductive elimination give you cross-coupling product here. Next, please. So we simply tested this reaction using ionic liquid. This is the original conditions of Sonogashira's conditions. Palladium tetraxphosphine, tetraxtriphenylphosphine palladium complex with kappa iodide, which worked quite well. We got 91% yield of the product. And however, if we eliminate the kappa iodide here, the yield was just only dropped down to 30%. However, if we change the catalyst to palladium dichloride, bisphosphine complexes, we were delighted to know that even without the kappa iodide, we can get the 96% yield. And we will also check the BF4 salt as a reaction medium, but the result was inferior to PF6. So we decided to use this PF6 for kappa-free types of natural catalytic reactions. Okay, next please. So in this system, so as I told you before, by citing the Chinese chemist's work, so palladium dichloride species we use is insoluble to ionic liquid. However, upon heating, it can be homogeneous solution. And we confirmed this palladium carbon complex was formed in the system. We got a nice crystal structure of this palladium carbon complex. And we tested, if we use this complex, it works quite well under the kappa-free conditions. Next please. So these are the result of some synthetic scope. It works quite well using these conditions. Next please. And also we tested the repeated recycling study, and we noticed that in first round 96%, but second round 80%. So yield is going down. So soon my student noticed that air has a program to kill the catalyst. So this they tried the gas condition under nitrogen conditions, and the yield is keeping high. So so this is very important factor for the catalyst recycling study. Next please. So then we are interested in the use of carbon monoxide. So if we use carbon monoxide here, we should make aromatic acetylenic by a similar procedure. Okay, please. And there are several previous work of this type of three-component coupling reactions. However, they use triethylamine as a solvent. This is the key. So it's not a good system. So people don't use this system. So it's a challenge for us. Please. And we tested the reaction, and the triethylamine, when we use a 1.2 equivalent, it doesn't give a good result. But if we use a 3.6 equivalent of triethylamine here, using BMI PF6, we can get 82% yield of the acetylene ketones using BMI PF6 conditions, under these conditions. Next, please. These show some examples. Sometimes we use autoclave batch reaction here, and sometimes we need a fine tuning of the condition, like CO pressures, higher CO pressures, or changing the amine from triethylamine to NMS pterogens. Next, please. And also result, and in this case, having a acetyl group at para positions, we need more heated lower temperature, and the higher pressure gave a good result. So anyway, so fine tuning is necessary in each case. But anyway, so we are satisfied with all these results done in BMI PF6. Next, please. So this is a mechanism. I can skip this slide. Next, please. So then one day, so we saw that people use most frequently the BMI PF6, but if once we use the BMI PF6, it's a very sticky liquid, high viscosity. So we attempted to use a low viscosity liquid. Next, please. So we focused on this BMIM triplet. This tantalum may be this ionic liquid, low viscous. Next, please. For example, this is a bit viscosity data here. Toluene, benzene, cyclohexanol, BMIM PF6. And BMI trifluid. So BMI trifluid has a 52. Yeah, 52. This value is quite close to cyclohexanol. So not so viscous, very smooth liquid. So we tested this for the cross-coupling reactions. Next, please. And we found that this BMI trifluid is an excellent reaction medium for palladium-catalyzed cross-coupling reactions. So please have a look at this data. We stopped the reaction at the 50 minutes. And if we use a BMI PF6, 23% is yield at this stage. But if we use a trifluid, low viscous one, already 51% of the product is formed. So reaction is very rapid if we use a low viscosity ionic liquid, such as BMI trifluid. Next, please. So we decided to apply this ionic liquid for some other cross-coupling reaction, like leukemia coupling reaction. It works quite well. Next, please. And also we tested for stereo coupling reaction, which combined real halide with organ tin compound. It also worked well with this BMI trifluid. Next, please. And we also tested for Heck reactions, and it also worked quite well. Next. However, when we applied to the reaction for the carbon-related Sonogashira type reaction, the BMI PF6 was better because this is a side product. Side product is a Sonogashira product. So Sonogashira product, Sonogashira reaction is very fast here if we use this one. So in this case, to suppress a competing reaction, BMI PF6 is better to use. Okay, next, please. In our laboratory, so we are interested in the use of carbon monoxide. So so far we made a lot of energies. We spent a lot of energies to develop new types of reactions. And the carbon monoxide is a very cheap feedstock. And this is a well-known, this slide shows demonstrated well-known Monsanto's acetic acid synthesis, which can convert methanol and carbon monoxide to acetic acid. So Monsanto's worker use a rhodium catalyst. Before Monsanto, BS's worker, BS's worker use cobalt, they have a patent. But anyway, rhodium is a good catalyst for industrialization. And here, the key reaction is a conversion of methanol to iode methane and then carbonation to give an acetyl-aldehyde. And then the hydrolysis give you acetic acid. So the problem here is if they use a higher alcohol, like propanol, and the reaction system suffer from the isomerization of the metal, whereby metal alkyl bond. So they got a mixture of the product. And also there is a serious problem that the alkyl halides are less reactive toward oxidative addition to metal center. So next, please. So we invented a new method without the use of metal system. Just we use photolytic conditions. Radical is formed, and you add to CO to form acyl radical. Then this acyl radical, if abstract iodine from alkyl iodide, it can give you acyl iodide. So this is a precursor to the ester and the amide. So we tested these ideas. Next, please. And there is very simple ideas. This idea contains two conductive reactions. One is a carbonylation. The other is an iodine atom transfer reaction from alkyl halide iodide to acyl radicals. Next, please. If we calculate by DFT method, the first step has no problem. this highly exothermic process. Next, please. However, the problem is the second step. In case of the alkyl iodide has a tertiary alkyl structure, it can work. But in case of the secondary or especially primary case, it's an energetically unfavorable process. So the second step has a problem. Next, please. So we circumvented this problem by using ionic trap by amine and alcohol in this system. So if we make amine and alcohol present this system, this acyl iodide once formed may be effectively trapped. So equilibrium is shifting to the desired directions. Next, please. However, limitation is here, primary case, as I told you. So this is not an easy process. So this, even we use a longer reaction time, like 50 hours, we got just only 54% yield of product. So we suffer from this problem with stress. However, if we add palladium catalyst here, so 12 hours, we got 87% yield. So in the presence of palladium catalyst, this reaction is accelerated. Okay, next, please. So this is a well-known dihydrocapsaicin. It contained in the hot pepper. So I decided to introduce this slide when I have opportunity in Korea. So anyway, so this is application to this short synthesis of this one by using starting from alkyl iodide, carbon monoxide, and the benzoic amine, and in the presence of palladium under irradiation conditions. It works quite well. Okay, next, please. And the secondary case, we don't need the palladium. However, so we are curious if the acceleration effect is observed or not. Please, next, please. So in case if we stop the 65 hours reaction time, so 50%. Of course, we use more than 10 hours, we can get a nice yield in the secondary case. It's a controlled reaction. And 65 hours without catalyst, 50%. However, if palladium catalyst is included, 91%. Next, please. So in case of tertiary case, again, next, please. In the presence of palladium catalyst, 80% is obtained. So acceleration is obvious even in the case of secondary and tertiary alkyl. Next, please. So since we use a palladium catalyst here, we tested BMI and tripling and as a palladium catalyst support here. So we use a palladium carbon complex again for this atom transfer type carbonation reactions. And it worked, and we got a nice yield of a secondary AMI, 87%, and the small amount of the double carbon product was also formed. And in the second run, 76% also yield a little bit diminished, so we need optimization anyway. So we made concept here. However, a very important thing is here, cyclohexane. We use cyclohexane for the extraction of this the product. Next, please. So, what's the problem here is solubility of ionic liquid to organic solvent. So, in case of BMI and PF6, cyclohexane, isopropyl ether, toluene, benzene, ether, the solubility is very low, always constantly low. But in case of BMI and triplyline case, if we use the ether as an extracting solvent for the product, it also extracts ionic liquid. So this is a disadvantage, but after checking the several solvent, and we found cyclohexane is very nice. So as long as we use cyclohexane as a extracting solvent, it isn't bothered by the contamination of the ionic liquid to the product part. Next, please. So another problem of the use of BMI filtering for this atom transfer type reaction is since this is a highly polar solvent, some polar reaction is completing here, like this one. So this is a SN2 type of product by amine lone pair attached to carbon here to kick out I minus. This reaction completes. So we have to be very careful if when associated with the use of ionic liquid, if the ionic reaction can complete, it's not the desired reaction. We have to be careful about this type of reaction. Okay, next, please. So let me change the topic here. So far, I discussed Pd-Catalyzed cross-coupling reaction can be carried out using ionic liquid, especially low viscosity ionic liquid. It's very nice reaction medium. So then we apply these reactions for microreactor type system. Next, please. So this is a chemical engineering meeting, so it's not necessary to make an introduction here. But anyway, so microchemical process has attracted a lot of attention recent years. There are several advantages over the conventional batch reactors. One is a high summary efficiency. The other thing is mixing is excellent. And the third thing is a ratio of surface to volume is very high. And the general reaction is fast, so the low residence time can be done and is achieved. Okay, next one, please. So to give you an idea, so I made this slide. If you use 1 milliliter of liquid, and if you use if you fill up this liquid to this 1 centimeter cubic style some reactor, and the wall, the area of wall is 4 square centimeters. But if you use 1 meter longs and this size is 1 millimeters, the wall area is 10 times 40. If you use 100 micrometers here, wall area is 400. So that means it's 100 times. So it's a big wall, always wall. Liquid, always contact wall. So that's why the thermal control is quite ideal, very ideal, unlike the batch reactor. And also the clever chemists take advantage of this very nice feature, as shown in the next slide. Okay, next slide, please. So this Henniges group in Germany made the microreactors, which this is a heterogeneous reaction, and the palladium is supported this wall using aluminum, and because of the very nice temperature control, they got the selective reaction. They would like to get monoolefins in this cell, and 90% it was observed. So this idea of how the heterogeneous catalysis can have a lot of advantages because of the microreactor systems. Okay, next please. So however, we thought even the homogeneous catalytic reactions, microreactor will have some advantages. Next please. So there are so many kind of homogeneous catalysis. And the next please. So and the as Professor Sedon's beautiful lecture told us, now the time has changed. We can use new reaction media, which can be replaced through volatile organic solvent, and the typically ionic reagents. Okay, next please. So as I shown in this talk, immobilization catalyst in the reaction media is very easy, and also separation is not difficult, even they use a homogeneous system. Okay, next please. However, sometimes we encounter solubility problem. So since organic solvent can make how to say completely homogeneous solutions. Okay, next please. So we thought microreaction technology would encourage this new trend in the organic synthesis. Next please. So I mean high-speed mixing and also continuous flow system. Okay, next please. So this is an idea. So substrate and catalyst mobilizing new reaction media come together, and in the flow system, reaction takes place. After that, separation, then the catalyst immobilizing new reaction media may be recycled. So this mimic heterogeneous catalysis. Catalyst and reaction media is immobilized. So we are very tempted to test these ideas. Next please. And I had an opportunity to visit Germany, to visit IMM, the pioneer in this technology, and I bought this tiny, very tiny micromixer after tough negotiation of the academic discount. And I brought back to Japan, and I asked my student to, okay, you should use this one for the reaction. And yeah, anyway, he did a nice work. And okay, next please. And this is a trick of mixing is here. They have 40 microns walls, and the A is coming from here, B is coming from here. But this is a fence, so it's not mixed. But there is a slit in the second floor. So like this. So this make automatically mixing. So at least 40 micro. So it's a very nice system for mixing. Next please. So we tested. We use this IMS micromixer, and my student did some of the coupling reactions, and he got the 93% yield of product. But this is amazing conditions. 0.1 milliliter per hour. Very slow. So anyway, so this may be the first report to report that the use of IMS micromixer for heterogeneous reaction in organic reaction. So they are IMS people are very happy about our result, but they just thanked to me by words, never said this mixer anyway. Okay, next please. So we tested just a T-shaped mixer having a 400 micrometer microchannel and 1,000 micrometer ones, and we recognize this the channels become wider, yield drop down. So there should be an effect of channel size. Next please. And these data here is all acetylenic compounds are made by the microreactor system in the flow system. Okay, next please. And of course, after the reactions, recycling is possible, but this is a manual working up. I will show you the automatic one later. Next please. So yeah, this is a case of Mizorok-Heck reactions, and the one from from one side, we use syringe pump, iodobenzene, butyl acrylate, tripropylamine. Mixture is coming from one side, and the other side, palladium-catalyzed solution is coming and mixed. And this is the residence time unit. We became clever to use a residence time unit, so the flow rate is increased 0.5 here. Anyway, so after the reaction, we got 87% of the butyl cinnamate. Let's freeze. However, so if we, as long as we use a syringe pump, so production is impossible. Okay, next please. So we purchased CPC's cytotherapy system, and we tested this one for the reaction, and we got nice yield. But there we encountered a problem that in case of BMI PF6, it's a sticky liquid, so pump is not enough. So if we switch BMI 3 low viscosity one, the stream was very smooth, and we got a nice yield of the product. Next please. So then we attempted to make a fully automatic system. So this part reaction can be done using CPC's microreactor system using pump, and then we challenge the extraction using this micro mixer, and the NaOH solution comes here and then mixed. Then the hexane solution is coming here and mixed, and we got a container containing 3 layers. In the bottom, from the bottom, we can recycle palladium. Next, please. So this is a target reactions. Next, please. We use a CPC system, then something like a homemade extraction system using a pump. Okay, next, please. And this is a Y-type glass tubes, and the palladium catalyst mobilized in ionic liquid is in the bottom, and then the water layer, and then hexane layer. Next, please. And we use another pump to transfer ionic liquid from here to here. Okay, next. And the student work 11.5 hours. So before, 10 years ago, maybe they worked harder. But anyway, so student quits the reaction, 11.5 hours to go back to their apartment. So I can stop. Anyway, so 1.15 gram product was obtained after the silica gel chromatography, huge silica gel chromatography. So anyway, that means 10 gram per hour. So we call this benchtop factory. Very small spaces, we can make product using this fully automatic system. Next, please. So, so we are happy to achieve the microflow system for cross-coupling reaction. Okay. So then the CO pressurized reaction is the next challenge. Next, please. So this is the devices we use. So maybe nobody understands this one. So, okay, please. So maybe this is better. CO syringe is here, and the mass flow controller is here, and pressure monitor is here, check valve is here, and CO is coming from here to here. And the palladium catalyst in ionic liquids comes from here to mix there, and then substrates mixed here, and residence time, and then the final product is obtained here. This is a pressure control valve, and to adjust the pressure, CO pressures. Okay, next please. So we got desired acetyl ketone 81% yield, and the result is will soon appear in the chemical computation. Next please. Okay, so, but we notice very important thing here. Very important thing here. If we use batch system under 5 atmospheric pressure, low CO pressures, we got 36% yield of the desired product together with sonogashira type byproduct. However, if we use microflow system under 5 atmospheric pressure, 92% yield of product is obtained. There is big differences. Microflow and batch. Next, please. So we check the generality. So we change some substrate, and we use a 3 atmospheric pressure CO, and always micro system is excellent. Always. Batch system always suffer from the production of the sonogashira reaction. Next, please. So usually we use a stainless steel stainless steel tubes, made tubes for the reaction, but we would like to see the inside, what's going on the inside. So I asked my student to use a Teflon tube, but it's really dangerous. Teflon tubes when it's not so strong for pressures. So anyway, so but he took photos, 3 photos. These are photos. Okay, in the first stage here, CO is here, ionic liquid is here. So it's a plug flow, gas leaking. And then the substrate is introduced here, and he took again the photos, and you can see substrate brown color here, ionic liquid is becoming yellow, and CO is here, again the plug flow. Then finally, in the end, brown colored solution and CO. So you can see the plug flow is constantly in this system. Plug flow, microflow is actually plug flow. Okay, next please. So what's the difference between microflow system and batch system? In microflow system, plug flow, and the channel rise is 1,000 micrometers in our experiment. So we can calculate the surface area volume ratios in microflow 20. But in case of using a conventional autoclave, the diameter is 2 centimeters. In such case, gas liquid surface area to volume ratio is 1. So 20 times of gas liquid surface area volume ratio. This may have something to do with the result. Next, please. So we, to test this hypothesis, we ran 3 experiments using the same concentration of alkyl iodide. Same concent, everything the same, but just we change the amount. So in the first case, 6 milliliter. The second case, 4.5 milliliter. The third case, 3 milliliter. And the rest condition the same. And we observed, in case of the final one, if we use a small amount of the solvent, total reaction mixture, we got very goodly, betterly. But if we use a large amount, we got poorly. So, next please. So I can summarize here. For ionic liquid case, surface to volume ratios directly connect with the result of the carbonation and carbonation ratios. But if we run the similar reaction using a DMF as a solvent, the result was always same. So this is a very important and also interesting findings in this carbonation when we use ionic liquid as a solvent. Next, please. Okay, this is the final slide. So let me summarize here. So we tested ionic liquids such as BM-IMPF6 and BM-NTF2 for palladium-catalyzed cross-carbon reaction. And the reaction works quite well. Especially we found low viscosity ionic liquid is a very excellent solvent for palladium-catalyzed carbonation reaction. Palladium-catalyzed cross-carbon reactions. And also these reactions can be successfully carried out using microreactors and the other reaction devices. Okay, next please. Okay, this is not my laboratory. So this is Osaka Castle and the famous in Japan but notorious in Korea Toyotomi Hideyoshi built this. But this is not the original one, rebuilt one. And inside there is an elevator, so even you don't have energy, you can go up see the area of Osaka. Next, please. Okay, this is a new building. Besides, it's contrasting. Next, please. And this is a beer, famous beer. So Kirin is a champion company in Japan. If you visit to Japan, maybe you see a lot of Kirin beer. And the Asahi was a bottom company before. But because of this dry beer, super dry, Asahi overwhelmed Kirin. So now it's a number. So it's competing, both. Both companies are very competing in Japan. So if you have a chance to visit Japan, please drink both beer and to judge which is better. Okay, next please. Okay, this is my group, and the next please. I'd like to thank Dr. Takahide Fukuyama. He's an assistant professor in my group. He did a very nice work in both ionic liquid and the microreactor. And I also thank Dr. Sifan Lee and Dr. Raman, and they are postdocs. And also collaboration with Professor Sato and the student for their hard work. I'd like to thank here. And also I'd like to thank for your kind attention. Thank you very much.